Okay, morning to all of you. In today we are going to take up a new topic which is known as fault simulation. Okay, what is fault simulation is we have a net list, okay, and also we have an collapsed fault list. So we know that for at each of these fault sites, okay, there could be n number of faults, but many of those faults can be collapsed by removing the faults equivalents and fault dominants. So that this is a minimum number of faults, right? Here at each fault site there could be two faults, right, stuck at 0 or stuck at 1, but many of them could be equivalent, and this we learned in one of our previous lectures, where in the previous class, where the total fault list can be collapsed and made a minimal list. Okay, so this is the minimum list which is available now, right? And also from our logic simulation class, we know, okay, what are the test vectors which are applicable for a particular net. Okay, now these three inputs are to be given into a fault simulator, and it is a part of the automatic test pattern generation, and ultimately I should have a fault statistics. Okay, now what is the fault statistics looks like? Right, it should say for a for an there's a lag. Okay, for a particular test vector t1, okay, for a test vector is nothing but combination of inputs. Okay, fault say 1, fault 10, and fault 11 will be detected. Okay, how is it detected? Because you will say, okay, for a circuit which is working fine, okay, that is no fault, the result should be known. Okay, that also becomes part of the fault statistics. Okay, that comes from the logic simulation, right? If there is no fault, the output z should have some value. It could be 0 or 1, and when I give an test vector t1, if the circuit has these many faults, okay, it will have a complementary of this available there, right? If it is the same, then obviously then these faults do not exist. Okay, it also means that then the fault statistics goes like that. It would be a matrix where it will be a list where I will have test vector 2 and say only fault 2 can be detected with that, right? And corresponding to that, the output, right, at the output, if there is no fault, what would be the output available? That data also should be there, if that output is, the expected output is not there, then what is the fault which gets covered? So there could be n number of test vectors, right? So these test vectors, first of all, for every fault node, there could be a fault site, there could be two faults stuck at 0 or stuck at 1, but 2 into n, where n is the fault sites, that may not be the entire fault list because it will be collapsed, right? And then here, for each fault, there may not be a corresponding test vector, because each test vector may detect multiple faults. Okay, so the number of test vectors will be still lesser. Okay, that's how we have an optimized. So the thing is, finally we should have a minimum number of test vectors, so that the testing is done in within reasonable time. Okay, so that is the target. This is like a very basic thing which is done, which is known as, if you take one stuck at fault at a time, first, this we learned in the last class also, we do fault sensitization. Okay, what is the fault, how is the fault sensitization done? Each node, if it is stuck at 0, you somehow give the input, we assume that there it would be 1, right? If similarly, if it is stuck at if it is stuck at 1, then we got to ensure that there is a 0 placed there. Okay, so that is a fault sensitization, and then you have to find a path where that fault is propagated to the primary output, right? And then from there you work backwards and you try to find out what are the corresponding input vectors. So these are the 3 steps involved. Okay, but this is taking one fault at a time, and if you keep doing this is known as sensitization, propagation, justification, SPJ. It's a lengthy process, right? So for each fault you need to do it separately, but every fault can be which is detectable, right? We said some faults cannot be detectable in case there is redundancy in the circuit. Okay, otherwise all faults which is not there is no redundancy, then they can be detected. So each of those faults separately you have to do SPJ. So this is a very lengthy process, so we should have something which is more time efficient. Okay, so what we do is we will learn those techniques soon, but before that there is something known as a random test pattern generation. We don't start, suppose it's an 3 input, so we don't start with 0 0 1 0 0 0 0 0 0 1. So such sequential testing from 0 increasing the value by 1, so that is not resorted to. Generally, if you have n number of inputs, there will be some random test pattern generator. Okay, so you keep generating those random test patterns, and you start and you give it to the fault simulator. Okay, so here, so I will have a random test pattern generator. Okay, so randomly some test patterns will be given to the fault simulator, and generally initially as the random test pattern and number of test patterns are increasing, the number of faults covered, okay, will grow at a good rate. So the slope will be very high, but as you keep coming towards the end of this fault coverage area, like towards from 70 to 100, so you will find that it is not getting picked. Those faults are not getting picked because it is difficult to get those faults, right? So you have to keep increasing, then you will have to keep running more and more test patterns to capture that, and it will be it will take a long time. So it would be better, right? Like when we make this fault list, okay, I will divide it into 2, okay, easy faults and difficult faults. Okay, so this how to classify this as a easy fault means easy to detect, okay, and difficult fault means difficult to detect. So how to classify these it as easy or difficult, that we will learn in the next class. Okay, so the first step, once you have the collapsed fault list, I divide that into 2. Okay, so this for the difficult faults, I will do this SPJ. Okay, I'll take one each of these faults, and for the easy faults, okay, I'll use the fault simulation software where I give the random test patterns, and each of those patterns will as you keep increasing the trial runs, okay, you take each test vector and run through the algorithm, it will keep covering one or more or many number of faults, and within a reasonable time you will find all the easy faults will get covered. Okay, is there any doubt still here? Any one of you, how this entire concept works? Yeah, Jay Singh, is it okay?
Okay, sir.
Okay. So let's see one of the first algorithms, how a fault simulation. So this is say the netlist, right? When you write the Verilog code, this is a fault-free code. Okay, this is available, right? And I can make one more block here, right? One I can write one. I can this is one circuit. Again, this is a same circuit here, modified to introduce one fault out here. Okay, can we do that? Say at particular any input point I want to make it stuck at 0. Can I modify the code so that this code has got that fault embedded into it? Can I do that? Yes, Ranjani?
Yes, sir.
Can we do that?
Yes, sir, we can do.
Last time I gave an example also, and for your assignment also it is like that. Okay, so so if there are n number of faults, so I need to write n number of codes, right? N number of netlist I will make. Okay, so there will be n different blocks out here. Each block will have one fault. Remember, all these things we are talking about single stuck at fault only, because earlier day in the introduction itself we discussed that multiple faults are not generally taken care of by all these algorithms, because you have most of the fab labs, it is not an usual thing to have fault. It is a rare case. So, and hence having multiple case, the probability is very less. So I have now this multiple blocks out here. Okay, now I am this test vector is coming from random test pattern generation. Okay, so I put some random test here. Okay, and I run first the fault free circuit. Okay, so I get some output, right, which I will save. Okay, now I take the second test vector. Okay, say no, the same test vector. The same test vector I am going to run here, right? If the output is different, what does it mean? If the output is different, right, what does it mean?
Fault is there.
Fault is there.
Fault is there, but as far as testing is concerned, what does it indicate to me?
Test vector is able to find that fault.
It is able to simulate that.
Yes, that test vector can detect that fault. Okay, now I will do I will apply the same test vector to the next block, to the next block, to the next block, to the next block. I'll complete the simulation. So one text vector itself, okay, at the run of at the end of this one particular run, okay, will it tell me, say this table is made other way around. Okay, but if I go if I make a table test vector wise, test vector 1, okay, it is detecting fault 1, fault 5, fault 6, like this. Can it give me this result?
Yes, sir.
Right?
How many fault it can detect?
Yeah.
By one.
Right? So then I change the test pattern, okay, randomly, the next test pattern, then again I do this run. Okay, so at the end of it, okay, the software says, okay, F1 fault, F2 fault, Fn fault, okay, that can be detected by these test vectors. Okay, now so this is the serial fault simulation technique clear to all of you, what it does? Okay, now if you see here, there are some additional things wherein we can make this slightly faster. First, it is an event driven. It will be like in the logic simulation class. I explained what is an event driven, right? So suppose I have, let me remove all this. Right? Suppose I have given 1 1 1 some test vector here. Okay. So this has already been simulated, the first block. When I'm coming from first to second block, okay, so so the results available at several nodes is already available to me. Okay, these available are. Now I am just changing somewhere in between, some data I am changing. These test vectors are also same. So I will take that change as an event. Okay, and I will again compute the output, right? So if this is in this chain, here all these places, right, there is no need to again recompute. So having an event, because only from when you are moving from here to here, only at one particular net some change is being introduced, right? When you are moving from here to here, this is being restored back, and another place some data, some new data has come in one particular fault site, right? So if you see, when you're moving from here to here, there are only minor changes. So what we learned in the last class, that event driven kind of simulation, right, will instead of an compiled code, every time you don't have to run the entire code. So this will save time. So is this okay with all of you? Do you all agree with me? If we have event driven, it can save time. Correct?
Yes, sir.
Okay.
Yes, sir.
Also, this is just an example given here, that suppose when I am running one test vector, if this fault is already recognized, okay, say in the fifth run, okay, in test in the fifth vector, F1 is detected, right? Then when I go to the sixth test vector, do I have to run this again on that particular block? No, right? It is already covered, right? So I will keep dropping those faults. Is it okay? Let me explain it once again. Say first run, okay, I have detected a fault and 5, a fault and 18 and something. In the second run, okay, I don't have to run that in the second test vector. This is a new test vector. I don't have to run that test vector on these blocks, CF5 and CF18, right? So because those faults have already been, we know that, so every time I don't have to keep, so as I keep changing the test vectors, the number of blocks on which I have to run will keep decreasing. Unless for a particular test vector, no fault has been detected, even that can happen in between, right? So that is known as fault dropping. Okay, that's all. That also speeds up on a fault simulation process. Is this also okay with all of you? Yeah, Tabrez, is it okay?
Sir, can a block has multiple fault?
No, each block will corresponding to one particular stuck-at fault.
Okay.
Right? It will not have multiple faults. Okay, so this is how this particular algorithm works. This is known as serial fault simulation. Why is it called serial? Because it is one test vector is taken, and serially this is you keep going down. Okay, this block and this block is not parallelly given the test vectors. Okay, so once this is the computation of this is done, stored, then a simulation of this is done, it is compared, and if it is detected, then it is removed from the fault list. Otherwise you keep it pending and you go to the next fault block. So serially one each will be in the next run. All those faults which have been detected, that will be dropped, and only which are pending, that will be taken. So it will keep moving like that. So this is known as serial fault simulation, right? Okay.
Sir, one question.
Yeah.
Yeah, so in this case, while dropping the fault, so let's say test vector 1 is able to detect F5 and F18, and test vector 2 is able to detect 5, 18, and 13.
Okay.
Then it's better to go with T2, right? Because T1 was only able to detect 2.
That compromise you have to do, right? Otherwise, what will happen? I understand you have a point that if I do a simulation of, say, I take one test vector, run for the entire thing. Take the second test vector, run for the entire. So it could be possible that T1 is doing 10, 11, 15, and 20. No, suppose T is doing 10 and 11, and say T100, okay, is doing 10, 11, and 100 faults, okay, 100, 150. So obviously choosing this test vector makes sense, because this is subset of this, right? So, but then the drawback in that is, like we are only, if you are talking about only 5 or 6 test vectors, it is okay. But suppose this is a 60-bit processor or something, right? So every time if you start doing that, then the test length, the duration of the test will go pretty high. Okay. So by fault dropping, like Lalit said, it is possible that this list what we are obtained may not be the smallest list. Okay, but time is a bigger factor. Overall, it will still save the time. Okay, Lalit.
Yes.
Okay. So this is like if there are no, n faults, right, and m test vectors, right. So there are m faults, so m block. There are if there are n faults, okay, total there will be n plus 1 blocks, because there will be one block which is free of fault also, right? And if there are total m test vectors, okay, say if it is a 4-bit 2 to the power of 4 m, total test vectors are there, okay, suppose it is there, then the maximum time for this simulation to complete will be m into n plus 1, right? But generally that is not the case, because what happens is many times each test vectors, more often than each test vectors will detect multiple faults. So this is the maximum time it will take. Okay, so but it will be much lesser than that, because so this is the algorithm finds those n vectors which are required, right? But it could be less than okay, I shouldn't have used this. Let me change this. For m is the maximum test vectors, n is the number of, while testing only n. Okay, it's okay. Right, these many runs may be required, and ultimately, okay, for each of these there are n faults. Ultimately, n vectors will be required, right? If each fault is being detected by only one test vector, okay. If there are no overlapping of test vectors for overlapping of faults for a particular test vector, then total number of final test vectors will be n, right? But otherwise, if for a particular test vector, if more than one fault is being detected, then it could be less than n, right? So total number of runs, max time will be this. Okay, those many runs will be required, and total number of test vectors finally maximum will be n vectors, because there are n faults. Corresponding to each fault, I should have one test vector. But then many faults will get clubbed by a single test vector, so it will be less than n. Okay, so this is how this serial fault simulation works.
Sir, can you explain that table?
This table?
Yeah.
This is just a sample table that the fault F1, right, is being detected by these faults, and fault Fn is being detected by 35 and 102.
But sir, it is told na ki if it is detected in fifth vectors, so we will drop that
No,
F1
that
block.
table for it was given in your textbook to explain this aspect, right? That if fault Fn is detected by vector 35, the simulation of the block Cfn is suspended beyond that vector. Okay, this is known as fault dropping. So they just put an example, right? Right. This is just to explain that. Okay, if you don't do fault dropping, then this is how the table looks like.
Okay.
Okay, so this is the thing which is given. This just an example given in your textbook. Without fault dropping, it will become like this. Okay, fault F1.
Okay.
So with fault dropping, you got to drop these. That's what it says.
Okay.
Okay. right? So this is how we insert a fault. So this is a particular fault site, okay, here for this. If I have to do that, right, instead of what I do is I insert an OR gate and an AND gate. So I have M0 and MZ as a control pin, right? So if I get give an MZ as 1, M0 as 0, right? So this is 1 and this is 0. So that means this becomes transparent. So this whatever data is available here, right? So since I am giving 1 here, the D whatever data comes here, since I am giving a 0 here, this data will come here, right? So this will operate like a fault free system, right? So whereas if I put an M0 is equal to 1 here, right? So this will give me 1 here. So it will simulate a stuck at 1 fault, right? Similarly, I put a 0 here. So irrespective of what, whether it is D or whatever it is, I'll have a 0 here. M0 is also 0. So this 0, 0 will bring a 0 out here, right? So these are the, instead of, right, making different blocks, right, you could also write a code for in each of the fault side. You could induce these 2 extra gates, and then when I'm moving from one block to other, okay, I just have to change the value of the MZ and M0. So automatically that fault will get simulated. Okay, so this is one way of so this is an so this becomes an easy for automation, right? So if you give the otherwise you'll have to keep thinking about it, but here if you have this as standard insert in all the fault sites, where this is the net and this is the node, so you could write a code to insert these 2 additional gates, okay, and then use this as an control inputs to simulate either there is a fault of 0, 0, 1 or no fault condition. So at each of this, so I have put it only in this particular fault site, okay, this so this needs to be done in each of the fault sites, okay, so we can do that. So this is how we can do the simulation. For your assignment, you might want to do this, or you can directly if you want to, because if you don't want this, since you have been told only at 2 sites, you can modify the code accordingly to directly put some faults there. Okay, so either way, that's fine with me, right? So this is the algorithm, right? You collapsed list is required, otherwise we'll be wasting time. Fault free simulation for all patterns. Okay, so this is required. The first run will be a fault free simulation, right? Because we have to compare. So the first here for each test vector, the first run will be fault free. So for different test vectors. So this is right. Then you take next, is it getting generated? Okay, and reset the pattern. Next pattern, and you keep changing the pattern, and you keep reducing the a fault for that. So delete the fault from F, right? If it is if there is mismatch, if there is a mismatch, that means that fault has been can be reduced from your list. Okay, so that it is no more to be simulated in the next run. So you run this algorithm. So this is just a graphical representation of what we discussed, right? This is another the same thing where a stuck at fault is there. So you are giving one test pattern here, right? This is getting generated, and if you are not dropping off that fault, you give the next test pattern. Again the same fault is being, this is fault free output. Okay, and you give the next pattern here, then the next fault is being detected here, right? So this is if you are doing fault dropping, then this won't be there in the next run. Okay, if you don't do fault dropping, then this will again keep repeating like this. So both options are available. If you drop the faults, then it will save time in generation that, right? If you don't do fault trapping and then later on you try to maximize that, in that case you might land up in having lesser number of test vectors. Okay, so the compromise is between how fast you want to generate the test vectors, or one and how small you want to generate the test vectors. Okay, how optimized result you want. Okay. So
Sir,
if you want to optimize
sir,
the results, then more time you have to give for the test algorithm. Yeah, tell me.
sir, in that if we are choosing fault drop,
Hmm.
then first run it will detect P1. Then if it will drop, then second it will drop. Then P1 will not be there. Then P2 will be there, na sir?
No. This is the test vector.
Okay, okay.
This is test
Ah,
vector. In
P,
the first run, KF will be detected. Okay. This
then
is the
both it will read.
fault.
Okay,
This is the
okay,
fault.
okay, okay.
Next
Ah,
run, if
okay,
you don't drop it, then again it will detect the same fault. Right?
okay.
Right?
Got it.
So it is a trade-off, right? Now, if you do fault dropping, right, the time for fault simulation will be reduced, but test vectors might be more, right? Because it is not an optimized thing, right? Right? But if you don't drop the faults, right, then it will the maximum it will run the all the test vectors, and later on you can optimize. You can see that what test vectors are repeating from the table what you get, right? You can you can do an optimization at that stage. Okay, that will give me an optimized test pattern, right? So that is there is a small trade-off there.
Okay, sir.
But generally fault dropping is resorted to. Okay, just pure by experience and statistics they feel that is better. Okay, right. So the advantages is it is easy to implement, ability to handle wide range of faults, right? Very fast combinational simulation. Disadvantages is many simulation runs are required. CPU time is prohibitive for VLSI circuits. Okay, so when we'll see that if there are several inputs, then it will take that much more time. So other algorithms we'll see today, which are slightly faster in nature. Okay, now we learn something known as parallel fault simulation. Okay, so suppose there are n number of faults. Okay, but this is essentially it takes advantage of the CPU registers. Okay, now let's take one particular CPU. It is a 3-bit CPU. Suppose I taken I'm example taking an 3-bit CPU, right? If I take a 3-bit CPU, okay, I will assign one register to each of these nodes. Okay, I'll assign one register. Okay, this is a register A, this is register B, this is register C, register D, okay, register E, register F, right? And it's a 3-bit CPU, so each register will have 3 bits. Okay, now the first bit of each register corresponds to a fault-free operation, right? Now, so I fill in an 1 here, I fill a 1 here. Okay, there is the next 2 bits. Okay, I can put one fault here, I can put the second fault here. That means this second bit will correspond to one fault. In this case, it is stuck at 0 at this particular point, right? And this is just an example. This is a stuck at fault at the other. So so there could be n number of faults in this particular circuit, but since it's an 3-bit system, right? 3-bit CPU, one got reserved for fault free. I have 2 empty spaces. In these 2 empty spaces, I can put faults, any 2 faults. So I have picked up these 2 faults for example. Okay, it could be any 2 from the circuit. So I have taken these 2. So the first bit for all these registers will be data will be the algorithm will run and it will fill in data for a fault free operation. So A is 1. So I take a test vector. First I will take one test vector, 1 1, right? So I'll put 1 here, 1 here, right? There is no fault here, so 1 is coming here. So 1 1 is 1 here. There is an inverter here, so this 1 becomes 0, right? And if you see here, this and this, okay, this data, because the CPU doesn't logical AND, all the AND operations will be done parallelly, correct? In one go, in one cycle of the CPU itself, right? So if you have understood how the CPUs work, right? If it's a 3-bit, all these operations will happen in a single. So there is no time taken to do OR operations in a single. It will do all these OR operations in one go. So 1 1 will give me a 1 out here. Similarly, this 1 0 will give me 1 here, right? Then in the second bit here, this is stuck at 0. So this continues to remain 1, this continues to remain 1, but in this particular register, this is becomes a 0. This second bit, because this is corresponding to stuck at 0. So here it becomes 0 here, and this is 1 here, so this becomes 0. So 0 0 will give me 0. Right, and the third register corresponds to stuck at 1 fault here. So at the input side, it doesn't make a difference. Here, I am considering only one fault at any given time, right? So the third bit here corresponds to stuck at 1 fault here. So there is no fault here. So this one which I am applying at B will be available here. So this will be 1 here, and hence this will be a 1 here. This should have been 0 here. Okay, but because of stuck at 1, I put this value in register in 1 here. So 1 1, and this gives me 1. So this is so in one single go, the CPU will update all the values of these registers, and this will be the value in the and the final in a register which is corresponding to the output C, right? So from this register, what can I say? Seeing the contents of this register, can I make some conclusions?
Stuck at 0 detected and stuck at 1 not detected.
Yes. So for this particular test vector 1 1, right? This has been detected and this has not been detected. Okay. So I get. So I have given test vector 1 1. So what will I do in the next run? What can I do? Anybody?
We can change the AB values.
Yeah, I can change the AB values, and what else should I do? I'll change the AB values, but what else? What about this? Can I take
the second bit.
I will drop this fault and I now take some other fault there. I'll retain this because this is not yet detected. Correct? Isn't it? Is it okay? Right? This fault has got detected, right? So I'll drop that fault and I will take some other fault in the circuit, right? So if you see here, this was an example for just for a 3-bit, right? Okay. So let me take one more example. Now this is an suppose this is an 4-bit processor. Okay. Now I can take 3 faults at a time. So suppose I have taken 3 faults. So this is my parent register. This is how I have done the assignment. This is no fault. Okay. This is the next bit stuck at W2. This is stuck at 4 here. This fault, and this is W1 stuck at 1 is here. Right, for these 3 nets. Now for 1 1, can I fill what is the data here at A? What will be the 4 bits? Can anybody prompt? If you can do it quickly, then we'll finish this slide. Otherwise, it will take a lot of time. You need to tell me what will be the 4 bits here. 1 1 1 1. Isn't it? Here at this node.
Yes, sir.
4-bit will be 1 1, right? Okay. At here, what will it be?
Should be 1.
110.
1 1.
Because it
0.
See, stuck at 0
Yeah, the
is
last.
at this position, right? So it will be 1 1 1
1110.
0, right? So what about this? This net will be 1 0 1 0 because this stuck at 0 is at this particular position, right? So I write 1 1 1 0 for this, right? So now, so this is how, so please understand how this is done. Okay, this stuck at 0 is taken here. For this, right? Why is it coming as 0 here, out here? Because this fourth says stuck at 0. That means this stuck at 0. If this is stuck at 0, obviously at this particular node also, I'll get a 0 here, right? So that is why I have to put a 0 here, right? So this is an inverter out here, right? So it is going to invert these datas, right? But there is an stuck at 1 fault also here, right? And that stuck at 1 fault is at the third bit position. So I insert a 1 here, right? This 1 1 1 0 should have got inverted to 0 0 0 1, right? But then this third bit, right, corresponds to stuck at 1 at W4. So and hence this is 1 out here. Okay. So this is how, so this is important from your exam point of view also. Okay. So is everybody clear how these 4 bits, all these registers get updated? Yeah.
So
can
number
you
of
repeat, sir?
registers,
A number of registers are?
no, sir, the number of bits in a register will be specified, sir.
Yes, that is depending on the CPU. If it is a 64-bit PCU, then okay, there will be 64. For a 4-bit CPU, there are 4.
Okay.
Okay. Yeah, Jesse?
Can you repeat again once, sir?
Yeah, sure. See, I am giving a test vector 1 1, right? So first is no fault. So here I will have 1. Second is W2 stuck at 0. So W2 stuck at 0. Okay. If W2 is stuck at 0, here it will continue to remain 1. It doesn't affect this net, right? Similarly, W4 stuck at 1. Okay. That doesn't affect this particular net, and W1 stuck at 0 also doesn't affect this net. So I write 1 1 1 here. Okay. Now that is done. Now I am coming here. This is no fault. I am applying a test vector 1 1. So this is also known. Okay. So 1 I am applied here, right? The next one is corresponding to stuck at W2 stuck at 0. Okay. This is right. It is already given this condition. So W2 is stuck at 0, but I am talking about this particular wire out here, right? So W2 stuck at 0 doesn't affect this point. So I am writing a 1 out here, right? The third one is W4 stuck at 1. This is stuck at 1. That is also not going to affect here. So I am putting a 1 here. Now the fourth bit is W1 stuck at 0. This. So this obviously this
that will affect it.
okay, it has got affected out here. Okay. So that is how I write here. Now, right now, this between this net and this net, okay, what is the difference? And I go from here to here. For this particular net, okay, here, okay, the first one is no fault, right? The second one is W2 stuck at 0. So this is stuck at 0. So I put a 0 here, right? Because if W2 is stuck at 0, it will be 0. Third one is W4 stuck at 1. So if this is getting stuck at 1, I am applying 1 here, it will come here. The fourth one is W1 stuck at 0. So if W1 is also stuck at 0, that also I will get a 0 here. So I put a 0 here. Is it okay now?
Yes, sir.
Right? So that's how we approach. Now similarly, this net is coming here. So this 110 comes as it is here. Now there is an inverter. So all these gets inverted, right? So 1 becomes 0. Okay, so it should have been 0 0 0 1, right? But the third one, okay, if you see here, it is stuck at 1 actually, W4. So if if that fault is there, then this is right stuck at 1 here. So this has changed to 1. So you need to make these all the registers will get updated accordingly, right?
We are looking sir forward wise. Like here, you told that W1 and W3 will be same value,
Yes.
and why not W2? Because that is
no.
there is
It's not yeah, because this stuck at 0 doesn't get reflected here. But
back. It will not go back side.
Yes,
Okay.
yes. Okay, so you have to take care of that.
Okay, sir.
Right.
Thank
So
you.
you update all the registers. Right. Why it is parallel? It's known as parallel because it is not that parallel. This one first bit and first bit AND operation is done here. What the CPU does is this entire register AND operation it will do in one go. That's how the CPUs work, right? When I say 8-bit processor, okay, if I do an OR operation, bit 0 to bit 7, I do OR operation with an A7 to A0, right? So it will do an bitwise OR, right? So here it is bitwise AND. So all of them will be done in a single clock cycle itself. It will just do the operation and give the result. So it is pretty fast because it is although hand calculation we might do 1 here, but these CPUs are will be handling all this as a single information and single in one clock cycle. It will do the bitwise and give this result in one go. Right. So here from the result, what can we infer?
Sir,
What are the
one
faults which are being detected at O1 and O2?
Sir, O2 last bit should be 0, right?
O2
Last bit, because we are ending 0 and 1.
Last bit corresponds to 0 and 1. Yeah. This has to be 0. Okay. Yeah. Okay. Thank you for that. Right.
So you
Okay.
can change the color also. Currently it is red, you can make it black.
Yeah. Okay. Since I'm taking this course for the first time and made the slides recently, there could be small errors. So your course can help me in refining this. Okay. Now, what are the faults which we took 1, 2, 3 faults, and I guess all the 3 faults have been detected, right? 2 faults has got detected in output O1 and 1 fault has got detected at output
Yes.
O2. Then I take a next test vector and I will take another set of faults. Okay. Now the max number of simulations, initially we said it was n into m, right? Now we can say that the total number of simulations required will be lesser by, you can divide it by w minus n roughly, okay, where w is the CPU word size. Correct, because those many, if w like it's a 4-bit, 3 faults are being taken simultaneously. Okay, so it can speed up, right? So this one can argue that it may be possible that all the faults are not getting detected. There is a possibility that some fault may not get detected and it can go into the next one. Okay, but in general we can assume that parallel processor will be faster. So by approximately w times. Okay, so just an approximation.
Sir, here M is I mean number of combinations of input vectors,
Yes,
right?
yes, yes.
So that will be like 4, and N is
N is the number of faults in the circuit.
number of faults. Okay.
In the circuit. Okay. Right? Okay. So the advantage of this is we can have a large number of faults are detected by each pattern. Okay. in the beginning of the test. Disadvantages only applicable for a unit or zero delay models. Okay, so if you have multiple delays, okay, so then this doesn't right. If you insert a delay model out here, then things may not work out here. Okay. Okay, in the two algorithms which we learned, okay, in the first algorithm, right, only one in one run, one particular fault was being handled. In the second run, a few more faults were handled based on the number of bits available in the CPU. Okay. So total it dependent on the register size or the bit size of the CPU. Now we have another algorithm here for a particular a test vector. All the faults which are applicable to that particular test vector in a single run it will do. So this is pretty speed. Okay, now how it does in the subsequent slides I will explain. Suppose this is the test vector. So first and foremost is I take a test vector 0 1, right? If I take a test vector 0 1, okay, here what is the fault which can be detected?
Stuck at 1.
Stuck at 1. So I write this, okay, LA. Now, LA indicates the a list of faults at node A. Okay, LA indicates, okay, a list of faults that can be detected at A. So A stuck at 1 can be detected, and LB means, okay, B stuck at 0 can be detected here, right? And what about here? Can B stuck at 0, can it be detected here for this particular test vector? Anybody?
Yes, if the A stuck at 1 is there.
Yes, yes.
No, I am giving. No, I am talking about these faults will be one at a time only. We won't have multiple faults, right? So analyzing is one. Like I am giving a test vector.
Difficult.
Test vector is 0, so I'll get this is 0 only I am getting, right? So even if it is stuck at 0, I can't detect that here. Correct?
Correct, yeah.
Right. So at this node, I can have A stuck at 1 or C stuck at 1 also I can find out for this particular test vector. Correct? If C stuck at 1, because I am giving 0 1, and this is the this notation we understand, right? I explained, right? 0 means for 0 1 I should be getting 0. If I am getting 1, okay, it means that either A is stuck at 1 or C is stuck at 1, right? B stuck at 0, I am not taking that into consideration because any one of these faults will be there at any given time. So since I am giving 0 here, I'll get a 0 here. So I cannot say B stuck at 0 or not. Okay, so I am not including that here. So this is the same wire which is going here. So here, apart from A, I am supposed to get here, but if I am getting a 1 here, that means D is stuck at 1 and E. So this is the list of faults that is applicable to this particular net E. Okay, this is the list of faults that is applicable to this. So is this much okay with all of you? Right now what we do is for each of these, once the netlist is given to the simulator, for each of these gates, okay, it will compute this particular list. Okay, and now you got to understand this particular notation very, very clearly. Union means either C is 1, okay, is detected, right, or A stuck in 1 will be detected, provided, right, there is no fault here, that this fault LB is not there, right? Because if this fault is also there, then can this A stuck at 1 be detected? It cannot be detected, right?
Yes.
correct? So this is how the simulator for E. Now if you see LA, okay, is specific for every time this LA, LB what we are writing, it is specific to this test vector, okay. When the test vector change, then the definition of an LA, LB here also will change, okay. So that we need to remember. LA doesn't necessarily mean A is 1, okay. LB similarly doesn't mean necessarily mean B is 0. It is A stuck at 1 for this particular test vector. So this is the notation which is written out here, okay. Now so the first thing from the net list, okay, it will compute this particular table for this particular AND gate, okay. So this is how it will move forward. Now when so in one go, okay, if you see here, two faults can be detected. So this way. So the property of this AND gate, okay. So this is the property of the AND gate. 0, 1, okay. This is universal property now. This particular what is written is an universal property of the NAND gate in the deductive fault algorithm. So this algorithm will say this is the kind of AND gate property. So once the gate properties are known, then we will see the entire circuit how it moves forward, right? Now I am giving a different test vector 1, 0. Okay, I am giving 1, 0 here. Then the fault list corresponding to A here will be A0 now, B1 here. Now here B1 and C1 can be detected here. Earlier, right, since this was 0 and 1 here, so A1 and B1. Now for this particular test vector, B1 and C1 can be detected, right? So for 1, 0, so this gets changed as an LB, right? And this fault should not be there, so I write LA bar. And now if you see the definition of LA here and here are different, okay, so that needs to be kept in mind. So now the definition, so this is for 1, 0, okay. Now similarly for 0, 0, this is 0, 0, okay. This is the third condition where stuck at 1 and stuck at 1. These are the fault list for these particular nodes, right? And here C equal, if C is stuck at 1, that can be detected, right? So that is the only fault that can be detected, right? Because there is only one fault occurring at any given time. So either this fault is happening or this fault is happening, but this fault can be detected by only C1, right? And the condition for that is LA and LB it should have been LA bar and LB bar for 0, 0.
Both A and B can be
Stuck at
detected.
1. Sir, but here we are taking two
Yes.
faults at a time. We are considering fault at A also and fault at B also.
Yes. So if both the faults are occurring at any given point of time, right, then I will detect it, okay. Or if only C1 is there, then I can detect it, okay. So that's how this is written, okay. That is an A fault is happening, along with that B is also happening, right. If both the faults are happening concurrently, and this fault is also happening, so this is the fault which would be there, okay. So this is the table for that, okay. So this is the expression which is written, okay. It means that
Sir, is it because the fault is same across A and B?
no, it's not because for each gate, right. So don't worry about these what is written here. What is important is the notation which we write in this table. This is how the algorithm would work. This algorithm says that, okay, if I am detect for a fault free operation I get 0, right. For a fault free operation I get a 0. For an if I am detecting 1, it means two things, okay. What does it mean? it means that there is a fault LA and there is a fault LB, or there is a fault C1. Is it understood? Right? These two faults are there and this fault is there. In the initial condition for 0, 1, right? For 0, 1, it means that this fault, if I am detecting 1 instead of 0, okay, that means that either there is a C1 fault or, okay, so if I am getting a 1 here, what does it mean? It means this is, I am getting, instead of 0, I am getting 1. So this is stuck at 1, but this is not stuck at 0. Okay. So that is the condition. Okay. So that is how this table is written. Okay. So these are the various conditions. Now for 1, 1, right, for 1, 1, if I see here, it means if I am, I should get a 1 here. If I am getting a 0, that means, okay, I guess I need to amend this. Okay. So here, if I am writing 1, 1 out here, right? So if I am getting an output and a 0 out here, right? It means C is stuck at 0, right? C is stuck at 0, or either C stuck at 0 is
Correct. And both A and B also stuck at 0.
Or A and B are also stuck at 0. Okay. So
Sir, here
no,
LA bar
A
and
or,
LB bar.
right? A
I
or,
think
it is
A-
not and. A or, right? Even if one fault is there, then also it will come to 0, right? So I am writing LA or LB.
But sir, at 1, 1, C will be 0, na?
Yes, C will be 0. C
Correct,
is
sir. Or will come. Yes.
right?
Yes, sir.
This is or. And this you mean to say C.
Sir, here in the table output C should have been 1, sir. That fault free output.
Here.
Yes, sir.
Yes, I think. This should be 1. Correct. Okay.
And so C1 should be 0.
Here.
Yeah.
Yeah, this should be 0. What? Let me just. Okay, this is for yeah, it is actually 0 here if you see here. Okay, 1, 1, C is 0. So there is an error out here. Right, I'll correct that subsequently. Right, this is C0, right? Union C0. Right, this has to be C0 because if it is a 1, 1, either C stuck at 0 can be detected. So this has to be C0 actually. So I'll change that before I upload it. Right. Okay. So similarly for an OR gate, if I give a 0, 0 here, right? So what will be the fault list out here? LA1, right? So this will be LA1, and if the output is 1, what does it mean? It is either A or B or C, right? So for 0, 0, okay, LA union LB, right? If this stuck at fault is there, or this stuck at one fault is there, or C stuck at one fault is there, right? So these are the for the other combinations also you could try that. So this is from our prescribed textbook. So these are all the various combinations for each of these gates. Okay, for a NOT, if it is an 0 out here and output is supposed to be 1, if it is 0, right? So it indicates that the output is stuck at 0, right? So similarly, if I am giving 1 out here, right, if I am getting, so this is for just for the NOT gate. So this table is important for you to remember, right? So uh, so for an open book exam, you might directly want to refer this, or for a closed book exam, then you might want to remember these things, right? So this is for now. If I have to if the circuit has to analyze, okay, for this particular circuit, what it does is it takes a test vector 0 here, right? And we already know the property of the for a NOT gate, when 0 is given, okay, it will refer back to the property of this NOT gate. When 0 is given, what are the at the output, what is the test faults which can be detected, right? So it will say, okay, at the output these are the faults which can be detected. Similarly, now I have a for a fault free operation, 1 0 is available here, okay, 1 and 0. Now it will refer to the AND table, okay, 1 0. For 1 0, it is an LB, right? For 1 0, right? This, now I have to write the fault location here also. So this A1 fault is coming here. So a union of these two, right? For 1 0, 1 0, it is this and invert of this, right? You take to take an union of that. So if I take invert of this, right, then A1 gets cancelled, right? Because in A1 is here, but I have to take for 1 0, right, invert of A1. So this is not more available. Okay, A1 will not be available. That means, okay, here A1, because it is an intersection of an invert for 1 0, right? So A1 goes away, right? Only B0 will be left, right? And then I have the for this AND gate, for 1 0, C1 is there, so C1 remains here. So this will from this table, okay, this table will be initially available with the tool, okay, for each gate, and this is the fresh net list we are providing. So it will apply these rules as it takes one test vector and keeps applying that rule. So in one run, okay, it will tell me, okay, these two faults can be detected at the output. Is this okay with all of you? So this table which is there, if I go back, this is the most important thing, okay, to analyze these kind of. So this table for each gate, okay, is already known, okay, for and this table is for different test vectors. So once you give that particular test vector, you have to see that. So this is how this does. Now for this is another example, okay. Now I am putting a 1 1 here, right? So for 1 1 for this particular AND gate, here, okay, this is just a net coming here. So B0 and C0 can be detected here, A0 can be detected here. For an AND gate for 1 1, now I refer back to that AND table. For 1 1, it is a union of this or this. That means all the faults at the input or the output will be available at the output. So referring to that table, so this is an OR of this and this. So all these faults are available here. So this is not again here. So at this place I have a B0 and this is a different D0, right? And this here B0 D0 will be available and F1 will also be available. That is coming from the NOT gate property, right? Then I take the OR gate, right? Now OR gate, fault free 1 0 is is coming here. So for OR gate 1 0, this is the property LA intersection LB bar. So this is A and LB bar. So if I say here, So B0 will be deleted from this list because I am doing an intersection with LB bar. So I need to remove B0. A0, C0, E0 will be available. So B0 will get eliminated. And then I have a union of C0. So I write C in this case is G out here, G, right? So you using this property of each gate. So in a single run, I will say, okay, 1, 2, 3, 4 faults can be detected. So this is how this algorithm runs. Is it okay with all of you? Right? It appears complex, but I suggest I have put 2 examples out here, and this table is available in your textbook, and these 2 examples are there. So if you try to analyze these 2 examples yourself, I think you will. So single vector simulation will give what are the faults that can be detected. Okay. And what should be the, and it will also tell you what is the correct result which needs which can be which is acceptable. Okay, so it will give this in a single run. Then you change the test vector, right? So here we keep changing the test vector. Now the only problem out here is disadvantage is right. It is very efficient, simulate to all pass. Okay, there is no, it doesn't save any time by fault dropping, right? So because every time a new test vector is done, it will compute this entire thing. Okay, so there is no concept of fault dropping here, right? So that is, so this is the algorithm. You can just graphical explanation of what we have done. So very efficient, simulate all pass right in one. Not easy to handle unknowns. Okay, that means in some cases, like in these algorithms, in the last, if some net value is not known to us for some reason, then it can't handle. Okay, it can only handle binary things. Only for zero delay timing model. Okay, and there could be potential memory management. Okay, so it will it keeps generating for each test run and all the this it will keep pushing into the memory lot. It consumes, this particular algorithm consumes a lot of memory. So these are some of the issues with. Okay, then there is an algorithm which is known as concurrent fault simulation. Okay, now what it does is I give a particular test vector. Okay, so each once I generate the net list, okay, it will generate the this is an AND gate. Okay, it will generate faulty gates corresponding to this gate. Okay, it will be there in the library. Okay, so it is not like instead of talking about each faults, right? For each node, say a node for a fault corresponding to a stuck at 0, right? It will create one gate in the memory. Okay, a faulty gate. Okay, similarly for B stuck at 0, it will create one more gate. Okay, and this is a behavioral model of the gate. Okay, it will be generating. So suppose I am giving 1 1 here, expected is 1 here, expected is 0 here, 0 1 is expected 1. So first simulation it will do 1 1 and it will give a result 1. Okay, in the next simulation it will replace this gate by this gate. Okay, this is known as a faulty gate. So first, once you give a net list to the tool will generate a corresponding behavioral model of the AND gate corresponding to A stuck at 0. So for A stuck at 0, how would this gate function? For 1 1 input it will give an output 0. Right? For 1 1 it will give a 0 because A is stuck at 0. So it will replace this model by this gate and again do a simulation. Right? So when it is doing a simulation, second simulation, what will be the final result? Right? It will give a 0 here. Right? 0 0 will give 0. Okay. Then it will since the result what we got is different from a fault free operation. Okay, it will mark that this particular gate, okay, A0 corresponding to the A0 stuck has already been, okay, detected. Okay, now in this that is the second run. In the third run, it will replace this gate, okay, the functionality of this gate by this gate, where B is stuck at 0. Again, the output will be 0. Okay, so I will get a 0 here, right? But this is a 0 here, right? So correspondingly, when I am simulating B is equal to 0, right, the model of this gate also will change, because now I am taking B stuck at 0. So if B is stuck at 0, it will be 0 here, it will be 1 here at the output, right? So I will have a 1 from here. So simultaneously, when I am taking this particular gate, first when I am taking this gate, okay, there is it is since I am simulating, it will take this normal gate only, right, for the first run. For the second run, when I am taking this particular gate, okay, for simulation, here this gate will be taken because B is stuck at 0. So now it has got faulty gates also model. So it will take this faulty gate model out here. It will push this model out here. So when I am giving a 0 here, I will have a 1 here. This is going to 0 here. I will get a fault. So I will. So this run will say B0 fault, B stuck at 0 fault, and cannot be detected by this test vector. Okay. Now I will go to the third condition of C stuck at 0, right? So C is stuck at 0. Can I detect that? So I am replacing this. So for 1 1 input, what are the total number of faulty gates which is possible? It can get stuck at 0. This can get stuck at 0, or this can get stuck at 0, right? Right, this C here it can get stuck 0, here it can get stuck at 0, here it can get stuck at 0, or here it can get stuck 0. So they are the only 4 possible faulty gates associated with this 1 1. For a different test vector, other gates also will be there, right? So this, for this particular 1 1 test vector, these are the 4 possible fault. Now I take the third one, right? And now third one is C stuck at 0, where B is not stuck at 0. So this will be taking as a normal gate. Okay. So I have a 0 coming here, 0 coming here. So I have a faulty output. So I'll say, okay, this stuck at 0 also can be detected, right? Then I move with a D. The next is a D, right? So when I take a D, right, and I am taking a fault at D, so this will be 1 from here, okay, whereas in D I am taking it as stuck at 0, so this will become 1 here, so that will not get detected here, right, because a 1 is coming from here, so actual required is also 1, so I don't get so this is so this fault cannot be detected. E is stuck at 0, so this E is stuck at 0, so this particular gate, it will be simulating this particular gate, whereas this will be fault free operation. So I have a 0 coming here for fault free operation, 0 0, whereas expected is 1. So I'll say, okay, this fault can be detected, right? F stuck at 1, okay, this cannot be again detected. G stuck at 0 can be detected finally, right? So if you see here, in a single run, okay, single run means single test vector, it will do simulations many times, okay, by replacing these gates with these are known as the faulty gate models, okay, for this corresponding to this gate, okay, for each fault it has got. So it will have more faulty models also, right? But for this particular test vector, these are the corresponding faulty gates. So it will put one gate at a time and do the simulation. Okay, one fault at a time. So when I take one fault, it will see, okay, where all which this is this needs to be replaced, or this needs to be replaced. Accordingly, those gates will be replaced, and it will be run. And in one go, it will say, okay, these faults have been detected. It will also say what are the faults which have not been detected and needs to be carried forward. Okay, so it also says, okay, this fault and this fault has not been detected. Okay, so so this is known as concurrent fault simulation. So then I change the test pattern. Okay, and I give the next run. Is this okay with all of you? Yeah, Ranjani, understood? Guessing?
Yes.
Okay. Okay, sir.
Right. So this is what. So once we give the net list to the in this particular case, like again this net list, okay, the tool will generate a faulty gates for the net list which is being given, right? So this is not a universal gate list, okay, that depends on the net list which we are giving to the tool. So it will see, okay, for these inputs, if this is the false, does this gate affected? If it gets affected, what will be the equivalent fault gate? Okay, it will first compute all the fault gates, right, for each of the gates the circuit, and then it will start simulating one each, and then it will do the, okay. Now it says, okay, only different parts of the simulate only different parts of the whole circuit. It is event driven, okay, for with fault tree, right? You can employ event driven for speeding up the operation, because when you are moving from one gate to other, a small incremental change is happening, right? The entire circuit. So when you are moving from one gate to other, so you can have an, you don't have to do again the compilation of outputs at each of these nodes, only where the change. So you can employ that even concurrent fault list for each gate. Okay, so that means all the faults associated with this gate and one each will be taken and resolved. Okay, it consists of set of bad gates. Okay, and fault index and associated with initially only contains local fault. So from the previous stage, okay, whatever faults has not got resolved will be propagated to the next stage. Okay, so these are some of the properties associated with concurrent fault simulation. Okay, so these are some other definitions in the faults you will find in the textbook. Events that happen in a good circuit which affects both good gates and bad gates. A bad event is events that occur in the faulty circuit of corresponding a fault. It affects only bad gates. Okay, so diverge means when we are moving right from one test vector to other test vector, new gates will keep adding up, right? Now if you see here, there are 1 2 3 4 bad gates associated here for test vector 1 1. Okay, now when I'm moving this test vector from out of which what happened, we have killed this gate, this is available, C0, this is also available, this is already done, right? Now and E0 also has got, this is not. So in the next run, okay, if I am changing this test vector to 0 and 1, this will be there, right? But corresponding to 0 and 1, there will be other faulty gates also. Will it be there, right? For 0 1, that means for 0 1,
Yes.
the faulty gate and a 1 1 1 output, whereas the fault will actually has to be a 0 here. So there will be a 1 1. There will be one more faulty gate. So for each gate there will be a few faulty gates. Okay. So as I move the test vector, okay, these will fall out, okay, and additional will keep coming in till all the gates are deleted. So that means it says that a few new bad gates can come, right? And also converge means, right, if you don't remove these fault gates, it is possible that in the next run these may not be detected. Okay, so one example is given here, right? So these were the bad gates in the first run 1 1, but now I move it to 0, right? Then these gates are not being detected, right? So that can happen. So obviously whenever we are moving from one test vector to other, those gates which have already been detected, you keep removing that. Okay, so that is the principle you have to do. Okay, and also these values, okay, when I am changing from 1 to 0, this is continuously remaining 1, right? So I can have an event simulation. So these gates need not change, right? This list of bad gates. So because it will speed up the simulation time, right? So because I'm making a change only here, I'm moving from this test vector 1 from 1 1 to 0 1. So I don't have to compute these again. Okay, the bad gates I don't have, but these bad gates will be required, because when I'm simulating this condition, okay, what is the output available here, that needs to be known, right? But you can use event driven simulation to save this, take this data from the previous run, okay, because this is not changed. So one corresponding to 1, this data is available, okay, and nothing is changing in this particular loop, so we can continue to have that. Okay, so that can be done. So this is a bad gates converging into good gates. Okay, so the bad gates which was detected earlier, now it is appear it's not being detected. So you need to avoid that situation. And this is like diverging bad gates. Like initially we did this. Now the test vector is changed, so you have additional gates coming in here, right? So that is known as diverging bad gates. Okay, so this is one. So the advantages, it is efficient, faults can be simulated in any modeling style, okay, and faster than other methods. Okay, again it requires more memory, right? Size of the concurrent fault list changes with runtime. Okay, these are the disadvantages. Now if you compare some of the things which we learned, serial will be the slowest one. Okay, then you have parallel, right? It will be slightly faster, and then you have the deductive, and this becomes the fastest. Okay, but memory usage wise, okay, then there is an issue. There is no memory issue with the serial and the parallel one, but these two algorithms, they will require larger memory space. Okay, and this is we will discuss this in very detailed, because present day this is the one which is most widely used. Okay, so in Boolean algebra, right, like we said, right, 0 1. Now what is this 0? It means, okay, fault free, it is 0, and 1 means there is an fault, right? Similarly at nodes I keep writing 1 0, 1 stroke 0. It means 1 means, okay, if there is no fault it is 1, and if there is a fault it is 0. So these two things we keep writing in circuits, right? But in Boolean algebra or when I do logic verification, now how can I represent 1 stroke 0 or 0 stroke 1? And there is no way, right? So so there is a total different calculus. It's not a Boolean calculus, right? Like when we learnt about the logic synthesis, right? Instead of 0 and 1, we took the values of z and x also, right, into the logic synthesis table, right? Similarly, this 1 0, okay, in roots D calculus, it is defined as D. Okay. So there is an it's not pure Boolean algebra, right? It also can compute the value of D also. Okay, and D is a single variable. 1 0 is defined as D, and D bar is defined as 0 1. So if this is stuck at one fault, right, it is actually, it should be 0, whereas stuck at fault means it is D bar, correct? Stuck at 1 means it is 1. So this particular condition, I can notate it as D bar. Is it okay? Why this D bar has come here? Right? It is a stuck at 1 fault here. That means 0. it should be 0, fault free. 1 means, so it is a notation. Now, for this particular condition, instead of writing a 0 stroke 1, if I write D bar, there is a calculus, there is an algorithm which will synthesize this. It will take D as a valid, D bar and D also as a valid input, okay, for the next gate. Okay, so D bar will get, it will come out here as D, right? Now D and 1 will give me D, and this is an OR, and I am having a 0 here, so I'll get a D here, right? So when I do the simulation, okay, if I am getting D out here or a D bar here, or for a fault here, okay, that means now I can detect this particular fault. Okay, this is how the Roth's algorithm calculus works, right? Suppose there is a fault out here, okay, which is stuck at 1 here. So this will be D bar, right? So it is an AND gate. So I have a D bar here, and this is a 0 here. This is 1 here. So 1, 1, 1 here. So output I will get 1. So at the output, if I am getting 1 here, right? I am not getting D here, then that means this particular fault cannot be detected. Okay, so this works on that algorithm. Okay, now that that algorithm, Roth's algorithm, okay, considers D also as an input. Okay, so this itself will take around half an hour to understand this particular algorithm. So I have moved this part into the next to next lecture. I will cover about the Roth's algorithm in detail in that lesson.